we state and discuss the rate distortion theorem. The proof of the theorem will be given in sections 8.4 and 8.5. We first define the information rate distortion function Ri of d. For d greater than or equal to 0, the information rate distortion function is defined by Ri of d equals minimum Ix x hat for x hat such that the expectation of the distortion between x and x hat is less than or equal to d. In the above definition, the minimization is taken over the set of all transition matrices Px hat given x such that the expected distortion between x and x hat is less than or equal to d, namely the set Px hat given x such that summation x x hat Px times Px hat given x times dx x hat less than or equal to d. Since this set is compact, that is closed and bounded in the Euclidean space, and the mutual information between x and x hat is a continuous functional of Px hat given x, the transition matrix, the minimum value of Ix x hat can be attained. Equivalently, the minimization can be taken over the set of all joint distributions Px x hat with marginal distribution Px, the given source distribution, such that the expected distortion between x and x hat is less than or equal to d. This is just another way to state the minimization problem. Since we have seen that the expectation of d tilde x x hat is equal to the expectation of dx x hat minus delta, where d tilde is the normalization of d, and delta does not depend on Px hat given x, we can always replace the distortion measure d by d tilde and the distortion d by d minus delta in the definition of Ri of d without changing the minimization problem. This is illustrated in the formula in definition 8.16. Therefore, without loss of generality, we can assume that d is normal for the purpose of defining the information rate distortion function. Theorem 8.17 is the most important theorem in this chapter, the rate distortion theorem, which says that Rd is equal to Ri of d. That is, the rate distortion function is equal to the information rate distortion function. That is, Rid is a characterization of Rd. We now prove a few properties for the information rate distortion function Ri of d. First, Ri of d is non-increasing in d. Second, Ri of d is convex. Third, Ri of d is equal to 0 for d greater than or equal to d max. And fourth, Ri of 0 is less than or equal to entropy of x. Compare with theorem 8.15 for the rate distortion function Rd, we see that these four properties are exactly the same four properties that we have proved for the rate distortion function Rd. The idea is that if Ri of d is equal to Rd, it has to satisfy the same four properties. We now prove theorem 8.18. Now, in the definition of Ri of d, the minimization is taken over all x hat such that the expected distortion between x and x hat is less than or equal to d. Therefore, property 1, that is Ri of d being non-increasing in d, follows immediately because for a larger d, the minimization is taken over a larger set. For the second property, namely Ri of d is convex, consider any d1, d2 greater than or equal to 0, and any lambda between 0 and 1. Let x hat I achieves Ri di for I equals 1 and 2. That is, Ri is equal to the mutual information between x and x hat I. And the expected distortion between x and x hat I is less than or equal to di. Now let x hat lambda be jointly distributed with x defined by the transition matrix P lambda x hat given x equals lambda times P1 x hat given x plus lambda bar P2 x hat given x. That is, the transition matrix for x hat is a mixture of the transition matrix for x hat 1 and for x hat 2. Then the expected distortion between x and x hat lambda is equal to lambda times the expectation of dx x hat 1 plus lambda bar times expectation of dx x hat 2 by the linearity of expectation. Since the expectation of dx x hat I is less than or equal to di, we have the upper bound lambda times d1 plus lambda bar times d2. And we call this d lambda. Finally, consider lambda Ri d1 plus lambda bar Ri d2. By the definition of x hat 1 and x hat 2, this is equal to lambda times I x x hat 1 plus lambda bar times I x x hat 2. Recall from example 3.13 about the convexity of mutual information that for fixed px, the mutual information between x and y is a convex functional of the transition matrix Py given x. And so we obtain the lower bound Ix x hat lambda. Since the expected distortion between x and x hat lambda is less than or equal to d lambda, the mutual information between x and x hat lambda is greater than or equal to Ri d lambda by the definition of Ri d lambda. Therefore, we have proved that lambda Ri d1 plus lambda bar Ri d2 is greater than or equal to Ri d lambda. This proves that RID is convex. To prove property 3, we let x hat be x hat star, the best possible constant estimate of the source variable x with probability 1. With this choice of x hat, we have the mutual information between x and x hat equals 0, and the expected distortion between x and x hat equal to d max. Therefore, the pair 0 d max is achievable. Then for d greater than or equal to d max, Ri of d is less than or equal to Ix x hat, which is equal to 0. Because Ri of d is a mutual information, it is non-negative, and therefore Ri of d is equal to 0. This proves property 3. To prove property 4, let x hat be x hat star of x, the reconstruction symbol that makes the distortion equal to 0. This is possible because the distortion measure d is normal. For this choice of the reconstruction variable x hat, we have the expected distortion between x and x hat equal to 0. Then Ri of 0, by definition, is less than or equal to Ix x hat, which is less than or equal to entropy of x because the mutual information between x and x hat is always less than or equal to the entropy of x. This proves property 4.